And the next speaker is Carl Luetzelschwab. I'll spell that phonetically. That's why Carl is up. Carl, one of my best friends up until right now. He's been writing about propagation for years and years. Contributes to the handbook, contributes to websites, contributes to NCJ, contributes. What do you not contribute to? I think it's probably a shorter list. Yeah. His talks are always well intended, and he uses many syllables. He's a wonderful guy. Carl.
Xenia. I always wondered why Xenia doesn't start with a Z, but we'll figure that out. Today didn't start too good for my wife Vicki is here, 89YL. They're coming out of the hotel. We saw an auction we had. He was trying to cross the road. Well, he didn't judge the speed of a truck very well. He got hit. So we ran over there and asked him, hey, are you okay? And he said, yeah, but I think I lost my life. So I said, well, are you sure? And he said, yeah, I'm positive. Now for the next speaker. Nathaniel, tough crowd here. Glad to be here. And how many were in the antenna forum or in Contest University saw Dr. Scone? Yeah. Her act is going to be tough to follow. Okay. So, well, we'll try and be going here. Hey, that's working good. Introduction to space weather and a little bit about talking about propagation. I only got 12 slides, so this is not going to be very deep. Hopefully, you can go find some books to read more about. Okay, I gotta use this. Oh, there we go. So what is space weather? Dr. Scove talked about that good, fairly well. Very well. And I think space weather is really non-terrestrial sources that impact the ionosphere. And of course, the quiet sun is space weather. The disturbed sun is space weather. Meteors, I kind of wrestled with that one, but of course meteors, come from outside our atmosphere and we collect them from around Earth, and that provides sporadic propagation. So that's kind of space weather too. Galactic cosmic rays, that's something. I don't know if anybody's been watching spaceweather.com, but they've been keeping track of galactic cosmic rays, and we'll get into that in the slides here down the road. Gamma ray bursts. Another source of space weather. It doesn't affect us too much, but we sure can see it. We'll look at that a little bit later too. So the quiet sun. Well, the quiet sun radiates at many wavelengths, right? Most of its radiation is at visible light. That's why our eyes seem to be in sync with the sun. It's 400 to 700 nanometers. But unfortunately, photons at those wavelengths can't do anything to the ionosphere. There's just not enough energy to ionize any atmospheric constituents. That comes from Planck's law and the ionization potentials of oxygen, electron, oxygen, whatever. So the true ionizing radiation is very short wave, basically from 0.1 to 121.5 nanometers. And I've listed the wavelengths that impact, that source the various regions of the ionosphere, F2, F1, E, and D. Just want to make a point that 10.7 centimeter solar flux, what we see a lot of, couldn't ionize its way out of a paper bag. Just remember that. It's a proxy for extreme ultraviolet, and mainly extreme ultraviolet, because mostly we're interested in the altitude for our activities as Okay, disturbances on the sun. That's a big source of space weather. Dr. Scove talked about that yesterday quite eloquently. She a solar heliophysicist. That's what we're together. It's really important. But NOAA categorizes three disturbances, and they abbreviate them G, S, and R. G stands for geomagnetic storms, and that comes from coronal mass ejections, CMEs, and also coronal holes, and cause the K index to elevate, and that screws up the ionosphere at times. S is solar radiation storms. That's when a big flare eject very energetic protons, relativistic protons. In fact, they're going pretty fast. And they funnel into the polar cap and cause increased polar cap absorption. So that doesn't affect us a heck of a lot, because most of our caps don't go across the polar caps. The notable exception is right around this time, 20 meters gets very good in India and everything, and that's because the polar cap is starting to get illuminated by the sun again and get the ionization up. So think about that. Radio blackouts, that's when a big flare ejects a lot of electromagnetic radiation at very short wavelengths. X-rays, that causes increased ionization on the day side of the Earth. There's a URL there. Once this is posted, go there, you can read all about those disturbances, how they're categorized, how they're labeled from 1 to 5, 1 being minor to 5 being really good. Meteors. That's interesting. The annual meteor deposition into the Earth's atmosphere peaks in the summer. Well, that's off Bell's head. That's when sporadic heat kind of has its best season. So there's some thought that that's what causes the seasonal dependency of sporadic heat. But, there's a caution here I read on the right that said, just because two things happen at the same time doesn't mean they're connected, so you've got to watch that. One of the things you have to look at is what about the meteor deposition in December? Because there's a minor peak in sporadic heat there. Does that cover that? But this is interesting to think about, and hopefully there'll be some more work on this to maybe explain why there is a seasonal dependence. I'm sure there's other people that can probably go much more deep than I can. Galactic cosmic rays, this one's getting somewhat more news in spaceweather.com. I'm not sure everybody's ever followed it too much. But what happens, there's galactic cosmic rays that we're just getting hit by all the time. When the sun's magnetic field is strong, like at solar max, that keeps those galactic cosmic rays out of our atmosphere. When the sun's magnetic field is weak, like at solar min, like that's where we're headed right now. We're probably a year or two away from solar minimum. More and more galactic cosmic rays are let into our atmosphere. And that's what that top plot shows. Remembering, okay, you take here's the,
Go to 6. You're on slide 6.
Here's the zero line. What we do is when galactic cosmic ray comes in, it's mostly very energetic protons from outside our magnetosphere, outside our solar system. When they come in, they hit atmospheric constituents, and they cause collisional ionization. One of the byproducts of that collision with galactic cosmic ray and atmospheric constituent is neutrons, and that's what we count are neutrons. The neutron counts correlates on the galactic cosmic ray circle. So you can see, what I said is when we have solar mass, when the sun's magnetic field is strongest, we should see the least amount of galactic cosmic rays. And we do. Here's the average count of cosmic rays here. So if we're below the average, if we're in negative territory, that means we're at solar max. And if above where it's solar wind, you can see at solar wind, the number of neutrons we're counting is increasing, which tells us more and more galactic cosmic rays are coming into our atmosphere. It also says that the sun's magnetic field has been weakening over several decades. Now, what does this mean? Well, if you take the ionization rate of galactic cosmic rays and kind of plot it and work it out, what it looks like is, here's a normal nighttime ionization profile. There's the peak at night. There's a valley above the evening peak. Then you go up and peak up region. It's not showing. But using those ionization rates, this is how many electrons those galactic cosmic rays add into the ionosphere. Well, that's not good for 160 meters because that's down at D region now where absorption occurs. So it's going to be interesting to see how everyone thinks 160 meters is going to be as we go through solar wind. A lot of work to do here. Again, just because it theoretically looks like it happens doesn't mean it's going to be a problem, but we'll find out. Gamma ray bursts, that's pretty interesting. Those are very energetic events. What I show here is a plot of the received level of a Hawaii transmitter on 21.4 kilohertz. Receiving in Boulder, you can see during the nighttime or during the daytime. Yeah, I guess that's daytime. It's before. Of course, the signal's stronger. No, it's weaker. And then at nighttime on this low frequency, the signal gets stronger. And here, right there, that's a gamma ray burst. What it did was ionize the D region so much that the signal dropped out. Well, think about that. You know, this originated in SGR, which is soft gamma repeater, whatever that number is, about 20,000 light years away. Now think about that. Something 20,000 light years away can affect our ionosphere. And you know, put that into context. What just something from the sun can do to us. It's amazing. We thought the Energizer Bunny was a lot of energy, right? Day-to-day variation of the ionosphere. One of the problems we have, Dr. Scove talked about, was we don't have a good handle on the day-to-day variation of the ionosphere. That's because there are really three sources that cause the variability in the ionosphere. One is, of course, solar radiation, that starts the whole process. But geomagnetic field activity, the Earth's magnetic field starts getting disturbed, that's going to affect the ionosphere by modifying the ionization. Now, there's another thing that we're starting to see a lot more technical papers on. That's events in the lower atmosphere coupling up to the ionosphere. For example, the earthquake in Japan, that caused their nuclear reactor to have a problem and all that. And the resulting tsunami that went across the Pacific, you can see the signatures of that in the F2 region. Really? Oh, okay. I thought you was disagreeing, and I stole my gun. Have you got a gun? Yeah, it's pretty interesting. And of course, volcanoes, you know, they can see signatures of volcanoes when they are up in the ionosphere. But that kind of, I agree. That's weird. But there's a lot more going on than we think. And I think we're starting to learn about it. Okay. The plot there is just something to show how bad this variation is. This is for the month of August 2009. That's every day of the month in August. During August, the 10.7 centimeter solar flux was constant, 66. It didn't go up or down, it was pretty much constant. There were 0 sunspots for that whole month. No sunspots. Okay. But the MUF over the Wallops Island ionoson varied by a factor of 2. And that, well, it's probably it's probably in those events in the lower atmosphere, coupling up to the ionosphere and modifying it. So a lot of work to be done here, and I think a lot of people are interested. Might even see a lot of this when the eclipse goes by. Yes, sir.
2009 was approaching the last solar mass.
Yes, that's right.
So
Yes.
it was not a phenomenon of solar wind, it was actually
Question.
okay, this didn't happen as we were going down toward the solar wind. It happened
Right.
as we were coming from the solar wind up to the solar mass.
But I'm not sure that how relevant that is.
Oh,
What's
lack of
relevant is
sunlight.
just, pardon?
The lack of sunlight.
Right, but
Don't you have that?
no, not really. Around solar wind, and there were lots of zero sunspot days.
Okay, but
We can-
2009 is approaching the max.
Oh, no, maximum was 2013 or something like that. That solar wind was very long. It was almost 4.5 years long. So we were still in
It was
solar.
closer to the max that you
No, it was closer to a minute. Never mind, okay. So what all this kind of suggests is there's a lot of work to be done before we can really model the ionosphere. And one of the things that I wanted to point out was that Josh, one of the speakers, he's over there in the back. He did get a grant from the New Jersey Institute of Technology to look at assimilating RV reverse beacon network data, trying to make the ionosphere more up to date than currently what it is, or more real-time ionosphere predictions. So, Josh, good luck to you. Characteristics of band. Well, to get a signal from point A to point B, how am I doing, Nathaniel?
wrap it up.
Okay, wrap it up. Okay, well, there's, kind of says what the bands are doing. What are we going to expect during the eclipse? Well, solar illumination will go away, so generally the lower band signal should come up, although there's a lot of variables there. Higher bands should drop out, but we're kind of near solar minimum, so we may not see much of that anyway to start with. A lot of other reports on solar eclipses. This is the 1999 one in the UK. And there's a picture of what the solar eclipse, where the totality line is, so you can line yourself up. Bill NQ6Z is working with the Idaho National Labs, right? He's working with the Idaho National Labs, Ionoson, which is right in the totality line, trying to get their Ionoson to take data more than every 15 minutes. Because every 15 minutes, it'll be over. Yeah, okay. Feedback. That's good enough. So, thank you very much.
While Nate's desperately trying to recover a video,